Greetings and welcome to Distillate. In the previous class, we discussed about material balance with chemical reactions. So in that, we discussed that if, let's say, this is my reactor, and in this reactor, I'm sending A, pure A. And let's take a generalized case. So let's say this reaction is taking place in this particular reactor. So you're going to get the A that remains unreacted and of course B, right? That's what you're going to get. So B that has been produced, right? So in a chemical reaction, you always know that the reactant is consumed while the product is generated, right? Reactant is consumed and product is generated. So on the basis of that, we make three equations for any problem like this. First equation is for A balance. All right, first equation is for A balance, in which we say that A in minus A out is equal to A consumed, right? Then the next equation that we make is for B balance. Now B is generated, right? So we say that B out minus B in is equal to B generated, right? B out minus B in is equal to B generated. And finally, the third equation that you make is from stoichiometry. The third equation you make from stoichiometry. So using stoichiometry, you basically relate the B generated term and the A consumed term. So we know that if, let's say, A moles of A react, then B moles of B are going to be produced. So if, let's say, if 1 mole of A is consumed, then that means B by A moles of B are going to be formed, right? B by A moles of B are going to be generated. So if I have Na moles of A Na moles of A that are consumed, then I'll get Na into B by A moles of B that are produced, right? That are generated. So in that case, I can say that B generated is equal to A consumed into B by A. All right, A consumed into B by A. All right, so these three equations we can form, and based on these three equations, we can follow material balance in a particular reactor, right? Then the next thing that we studied in the previous lecture was limiting reagent, right? So we discussed that if suppose we have a chemical reaction like AA plus BB gives CC plus B, right? If we have this as a chemical reaction, then that case the theoretical ratio, there's something called the theoretical ratio, which is basically the ratio of A to B, right? So A by B is basically the ratio of theoretical ratio of A and B. That is the theoretical ratio of both the reactants is basically the ratio of their stoichiometric coefficients. So stoichiometric coefficient of A upon stoichiometric coefficient of B. All right. Then the second ratio is the supply ratio, which is basically your A supplied upon B supplied, right? So that is basically the number of moles of A that have been supplied upon the number of moles of B that have been supplied, right? That is your theoretical theoretical versus supply ratio for A and B, right? So that's how you do the calculation for these two ratios. Now, remember, when we calculate these two ratios, then we have two possible cases. Actually, there are three possible cases. First case may be that theoretical and supply both are equal, If both are equal, then none of them is a limiting reagent. All right, neither A nor B is a limiting reagent. But let's say if I get my theoretical ratio lesser than the supply ratio. All right, if I get my theoretical ratio lesser than my supply ratio, then in that case, I'll get my denominator. My denominator would be limiting. All right, my denominator is limiting. All right, if my theoretical ratio is lesser than supply. So in this case, B is going to be limiting. All right, and let's say if my theoretical ratio is greater than the supplied ratio. All right, then in that case, my numerator is going to be limiting. All right, my numerator is going to be limiting. All right, so that is A. A is going to be limiting in this case. All right, and third is of course that if both are equal, then there is none of them which is limiting, right? Then we studied that if a particular in a particular reaction, one reactant is limiting, and the second one is known as the excess reactant, right? So if A is limiting, then B is going to be the excess reactant. So we are going to go with the case that A is my limiting reactant. So if A is my limiting reactant, then B is going to be the excess reactant. All right, B is going to be the excess reactant. So in that case, we define another term which is percentage excess. So percentage excess is basically the moles of B supplied minus moles of B theoretically required upon moles of B theoretically required. All right. So how to calculate the moles of B that are theoretically required? Whatever are the moles of the limiting reagent. Let's say there are 10 moles of A. So in proportion to that, if we consider stoichiometry, in proportion to that, how many of moles of B are needed to exactly react with these many moles of A, right? So that will give you the number of moles of B which are theoretically required. All right, this term is very important. Theoretically required. We will see why. So theoretically required is basically the number of moles of particular reactants that are required to react with the limiting reactant. Okay, exact number of moles that are required for a particular reactant to react with the limiting reactant. All right. So B supplied minus B theoretically required upon B theoretically required into 100% gives us the percentage excess of B. All right, that gives us the percentage excess of B. And from here, we derived another thing, that is, if Bs is the number of moles of B supplied, then that is going to be B theoretical times 1 plus percentage excess by 100. So I gave you an example that let's say if you have 40% excess, if you have B that is in 40% excess, then that is going to be 1.4 times B theoretical, because here you'll put 40. So 1 plus 40 by 100, that is 1.4 into BTH equals to BX. So percentage excess can also be greater than 100. That's no question, right? So it can be greater than 100 as well. All right. Then we defined another term that was specifically for limiting reagent. That was percentage conversion, right? So limiting reagent in this case is A. So we are going to say A supplied minus A left upon A supplied into 100. All right, that gives us the percentage conversion, right? So let's say if A left is 0, all of A has been converted. So in that case, A supplied by A supplied is 1. So the percentage conversion becomes 100%, right? So in order to calculate percentage conversion, let's say if this is my reactor, This is my reactor, and let's say I'm supplying 100 kilomoles of A, right? And from here, I'm getting, let's say, 10 kilomoles, right? So in that case, percentage conversion of A is going to be A supplied, that is 100, minus A left, that is 10, by A supplied, that is 100, into 100, that gives us 90%. All right, that is the percentage conversion. All right. So once you're clear with all whatever was done in the previous class, previous video lecture, so now we move on to a problem. So this problem, it came in GATE 1992. The analysis of gas entering the secondary converter in a contact sulfuric acid plant is 4% SO2, 13% oxygen, 83% nitrogen, volume percent. That means mole percent. In converter, SO2 is oxidized to SO3. The gas leaving the converter contains 0.45% SO2 on an SO3 free basis. That means if we do not consider SO3 in the analysis, and apart from SO3, all the other gases that are there, if we consider among them, then SO2 is 0.45%. So calculate the percentage conversion of SO2. So go ahead, pause the video, and try to solve this problem yourself. Hope you could solve this problem. So let's discuss how this is going to be solved. All right. You might have faced certain issues. So let's just make it clear. And even if you have solved this problem, still you might have done it a longer way. So I'll give you certain ways. You might find this easier. So let's see. So first of all, we'll draw a block diagram. So we have the secondary converter. Now remember, when you're solving a gate problem, so you might want to reduce the number of steps, right? Number of steps that you're writing. So over here, I'm trying to explain you people how to solve a problem. So I'm going to write down each and every step. But if you feel that a particular step is unnecessary or something extra, then you can omit that step, right? For example, I'm writing the stoichiometry at every point. So stoichiometry is quite important. But if you know the reaction, if you can mentally calculate all these things, so you don't need to really write the stoichiometry at every step. Okay, so that's there. So try to avoid too many steps in order to solve the problems easily. All right, and in order to avoid consuming too much time writing. So we have the secondary converter. In the secondary converter, we send the feed. Feed contains SO2, 13% of oxygen, and 83% of nitrogen. So we are going to take our basis as, the basis that we are going to take is that we have 100 kilomole of feed, right? So it's 100 kilomole of feed, therefore you'll have 4 kilomole of SO2. In the feed, we have SO2, oxygen, right, and nitrogen. So we have 4 kilomole of SO2, then oxygen is 13 kilomoles, and nitrogen is 83 kilomole. All right. So once you're done with this, then we'll go to the product side. On the product side, we'll get SO3, unreacted SO2, unreacted oxygen, and unreacted nitrogen, right? So nitrogen, whatever was there, it will be here as it is, because this is not involved anywhere in the reaction. So if it is 83 kilomole over here, then it is going to be 83 kilomole over here as well. All right. Then the next thing that we have to deal with is the stoichiometry. So the stoichiometry of this reaction is 2SO2 plus oxygen gives you 2SO3. So as you can see, there is no nitrogen over here. That is why I've directly written nitrogen as 83 kilomole here. All right. Let's say if I was sending something else, suppose let's say, this is not a part of the question, I'm just saying, let's say I would have been sending 100 kilomole air, all right, from this side, right? So if I'm sending 100 kilomole air, then along with that comes 79 kilomole of nitrogen, right? 79% nitrogen, 21% oxygen. 79% of nitrogen would have been added. So here we would have got 83 kilomole plus 79 kilomole. All right, because this is the total input of nitrogen. But for the time being, that's not the case. So we'll just avoid that. Okay. So this is the stoichiometry. 2SO2 plus oxygen gives you 2SO3. All right. From the stoichiometry, you can clearly see that if you have 2 moles of SO2 react, then 2 moles of SO3 will produce. And in that case, only 1 mole of oxygen is going to react. Right. Right. So we are going to consider reaction of 2 moles of SO2. So we initially have 4 kilomole SO2. We have 13 kilomole oxygen, and we have 0 kilomole of SO2. All right. So in that case, when we, let's say we are reacting. So remember, if let's say X kilomoles of SO2 are going to react over here, then X by 2 kilomoles of oxygen are going to react. Right. Now a fraction, try to avoid fractions as much as you can. So a fraction here, it would make your calculations difficult, right? So instead of taking X kilomoles of SO2 have reacted, we are going to take 2X kilomoles, right? We are going to take 2X kilomoles of SO2 have reacted. So if 2X kilomoles of SO2 have reacted, then we'll be left with 4 minus 2X, right? And over here, let's write it here. See, this was the initial condition that was towards the input, right? Now, after the reaction, what happened? Since 2x kilomoles of SO2 have reacted, therefore, you have 4 minus 2x. All right. So when 2x kilomoles of SO2 will react, naturally, half of them, that is x kilomoles of oxygen would react. So oxygen left would be 13 minus x. All right. And if 2x kilomoles of SO2 will react, then 2x kilomoles of SO3 will be produced. So this is going to be 0 plus 2x, right? So here we'll have 2x. Here we'll have 4 minus 2x. And here we'll have 13 minus x. So see, if you do a problem this way, so it would avoid fractions as much as possible, right? That way your calculations are going to be easier, right? Your calculations are going to be easier. So that way. Okay, so once we have this in hand, now we know that SO2 is 0.45% in an SO3 free basis. So if we leave SO3, then apart from that, if we consider all these, okay, if we consider all these, then for a 0.45% of that is SO2. All right. So that means let's call them all P. So 0.45%, that is 0.45 by 100 into P is equal to whatever is SO2. So SO2 is nothing but 4 minus 2x, right? Now what is P? P is basically the sum of all, right? So it's going to be 83 plus 13, that is 96, plus 4, that is 100. All right. So this is going to be P is going to be 83 plus 13 minus 2x plus 4. I'm sorry, 13 minus x. Right. So this is going to be on an SO3 free. So 83 plus 13 minus x plus 4 minus 2x, right? That is going to be your result, right? 83 plus 13 minus x plus 4 minus 2x. That is going to be your total. All right. Now, since we have P, So we are going to substitute it over there. So that is going to be 0.45 by 100 into 100 minus 3x is equal to 4 minus 2x. So simplifying, we'll get 45 minus 3 into 0.45, that is 1.35. X is equal to 400 minus 200x. Now this 200 we'll send here, 200x, and 45 we'll bring here. So we'll get 200 minus 1.35, that is 198.65x, right? And then we are going to take 400 minus 45, that is 355 over here. So on the basis of that, we'll get x as 1.787. All right. So once we get 1.787 as x, so SO2 that we are going to get, SO2 out, is 4 minus 2x, that is 4 minus 2 into 1.787. So that is equal to 0.426 kilomole, right? That is SO2 out. Okay, that is SO2 out. So percentage conversion is equal to SO2 SO2 in or SO2 supplied minus SO2 out upon SO2 supplied into 100. So SO2 supplied is 4, SO2 out is 0.426, and SO2 supplied is 4 into 100. So that is going to be 89.35%. This is your answer. All right. This is the answer. 89.35% is the conversion. All right. So once you are done with this problem, hope all of you could understand. What we did in this problem was basically we assumed that the conversion, or basically 2x moles of sulfur dioxide are reacting. Why we took 2x moles? So that we could avoid fractions over here. Otherwise, if we would have taken x moles of SO2 have reacted, then we would have got x by 2 over here. So in order to avoid that, we took it that way. All right. So remember, try to avoid fractions as much as you can. Okay. So once you people are clear with that, then we have calculated our problem. So since we knew that for 0.45% was SO2 on an SO3 free basis, so we simply calculated the total products, the total moles of products without SO3. So that came out to be 100 minus 3x, right? And based on that, we calculate 0.45% of that, and that we equated it equal to 4 minus 2x, which was the kilomoles of SO2. All right. So when we solved, we got x is equal to 1.787. When we substituted x equals to 1.787 here in place of SO2, then we got SO2 as 4 minus 2x, that is 0.426. Then percentage conversion is equal to supplied minus left upon supplied into 100. So that is 4 minus 0.426 upon 4 into 100. That came out to be 89.35%. They could have asked you something else. For example, they could have asked you that what is the amount of SO3 that is produced. Or they could have asked you what is the mole fraction of oxygen in the outlet gas mixture. So anyways, once we have got this x, the starting would have gone the same way. We would have found x. All right. Now, once we have found x, then we can find anything. We can find 2x, we can find 4 minus 2x, we can find O2, that is 13 minus 6. Anything can be calculated from that. And once we get that, then we can calculate anything else. All right. For example, the composition on a mole basis, total weight, anything, whatever they ask you, you can calculate. All right. So that is the calculation of x is the main thing. Once you get x, then there's nothing else. All right. So once you're clear with this, now we are going to do a very important topic, that is application of material balance in combustion. This is a very confusing topic. A lot of equations, a lot of stoichiometric equations are formed in this particular topic. So you need to be very clear with what we are doing. All right. You need to apply all your stoichiometry, material balance, all that you have to apply it over here. All right. So this is basically a kind of practice of whatever we have learned till now. So please be sure that you're totally clear with whatever we have done so far, so that you're able to attempt this topic. Otherwise, the people are going to be very confused now on. So please make sure that you are clear with whatever we've done so far. All right. Go back and watch the videos again so that you're clear with whatever has been done so far. All right. So once we go on with, after that, we move on with combustion. So first of all, let's understand what's fuel. Fuel is something that produces large amount of energy on burning. That is known as fuel. All right. For example, coal, petrol, diesel, kerosene, methane, ethane, etc. These all are fuels. All right, because they produce large amount of energy when they are burned. All right. So fuels are very important because industrially they are used to supply energy. All right. For example, there are a lot of industrial equipments that need heat, that need energy. So, for example, boiler or sometimes even heat exchangers, all those need fuels. All right. They need energy, they need heat energy. So fuel is used. Fuels are used in that case to calculate or to get the energy. All right. Even in cement manufacturing, we have kiln that is fired by fuels. All right. So fuels are very important. All right, very important, and a proper study of fuels is very important. All right. So fuel may be solid in nature, for example, coal. It may be liquid in nature, for example, petrol or diesel. It may be gaseous in nature, for example, methane, natural gas, producer gas, water gas. All right, all these are fuels. All right, so they can be solid, liquid, or gaseous in nature. Then we come to combustion. Combustion is basically the process of burning of fuel in presence of oxygen to produce energy. All right, process of burning a fuel in presence of oxygen to produce energy is known as combustion. Now remember that a fuel, one of the major components of fuel is carbon. So when carbon reacts with oxygen, there are two possibilities. One, it may form carbon dioxide. And the second possibility is that if oxygen is limited, all right, in that case, we might get carbon monoxide. All right, so these are two possibilities. And the second thing that is present in fuels quite a lot is hydrogen. You know, you saw methane, ethane, natural gas. So all these contain hydrogen. Methane is CH4, ethane is C2H6. It contains hydrogen. So hydrogen in the fuel, it reacts with oxygen to produce water vapor. All right. Now water also has a very important significance. We'll just discuss this further. So basically, this is what your combustion looks like. All right. So when combustion takes place, that is burning in presence of oxygen, that is combustion. So when oxygen is sufficient, then the combustion is considered as complete combustion. All right. And in that case, the products of combustion would include carbon dioxide and water. All right. Water is going to be there irrespective of complete or incomplete combustion. All right. And if there is incomplete combustion, that is, oxygen is limited, oxygen is present in a limited amount, or less oxygen is able to contact carbon or contact fuel. So in that case, the combustion is going to be incomplete. All right. And in that case, the products of combustion would include carbon monoxide and water. All right. You may get a combination of the two. You may get some percentage of carbon dioxide and some percentage of carbon monoxide. Now, whichever will be in majority, that particular combustion would have taken place maximum. For example, if carbon dioxide is more, then complete combustion, most of it would have gone through complete combustion. And if carbon monoxide is more, then in that case, most of it would have got less combustion. All right, incomplete combustion. All right, so that's how your entire process of combustion goes on. All right, so it's just these stoichiometric equations that you need to keep in mind. All right, we'll study further how are they important, but for now this is what we need to know. All right, then we come to a very important concept in a fuel. See what happens when a fuel it burns, it releases energy, right? That is the definition of fuel. So the basic what fuel is used for is to release energy. So what is the most important quality or most important characteristic of a fuel? It's obviously going to be the energy it releases, right? If I have, let's say, 10 kg of fuel and it releases 500 calorie, 500 not calorie, kilocalorie. If it releases 500 kilocalorie of energy, then that is going to be really good. But if let's say we have 10 kg of another fuel and it releases only 100 kilocalorie, then that's going to be less better income. It's going to be less important or less effective in comparison to the other fuel. So energy is the most important characteristic. So the energy released by a fuel, that is basically your characteristic that you need to see in a fuel, right? So calorific value is basically that characteristic. All right. So the energy released by a fuel is measured in terms of its calorific value. All right. So we'll discuss in thermodynamics about heat of the reaction. So in that you'll be able to understand what the basic of calorific value is. Just understand that if a particular reaction takes place, takes place, then there can be two possibilities. The first possibility might be that the reaction it releases heat. All right, the reaction it releases heat. This kind of a reaction is known as an exothermic reaction. All right, this kind of a reaction is known as an exothermic reaction. The second may be that it absorbs heat. All right, it absorbs heat, or you need to supply heat for that reaction to take place. So that kind of a reaction is considered as an endothermic reaction. All right. So in an exothermic reaction, heat goes out. Heat it goes out, and in an endothermic reaction, heat it comes in, right? In exothermic reaction, heat goes out, and in endothermic reaction, heat comes in, right? So what happens if we consider a combustion reaction? Then that is an exothermic reaction, of course, because it is releasing energy, right? So it's an exothermic reaction. So when it releases energy, right? So the heat that is released for a combustion reaction to take place, that heat is known as its calorific value, right? That heat is known as its calorific value. Okay, so this calorific value is basically heat released when the combustion reaction takes place. That's it. All right, we'll study in thermodynamics more about this. For now, just understand that if a combustion reaction is taking place, then whatever is the heat that is released in that reaction, that is known as the calorific value of the fuel. All right. Now, this calorific value can be measured in two ways. First is gross calorific value, and the second is net calorific value. So we discussed that the fuel, when it is burned in presence of oxygen, it gives you carbon dioxide and water, right? Now, this water, it may be in liquid state or it may come in vapor state. All right. So what happens when this water, it comes in liquid state, then the heat that is released by the reaction, is known as gross calorific. So when this water is in liquid state, then it is going to be, the heat of the reaction is going to be the gross calorific. All right. Now, if let's say water in this liquid state it takes up some of this heat. It takes up some of its heat and converts itself into its vapor state. All right. So now, since water, the system itself took some of its heat, therefore, lesser heat would be released. Lesser heat would be released. All right, because some of the heat that was released, it was taken back by the system. All right, just understand. Suppose if you are taking out your wallet and you're spending, let's say, 10 coins. All right, you're spending 10 coins. Now, if you take 2 coins from that wallet, from that a bunch of 10 coins, and you put it back inside your wallet, so in that case, the net amount of coins that have gone out from your wallet, that are just 8 coins, right? That are just 8 coins. So if you use those coins, use the 2 coins that you have given out. So that is going to be lesser. The coins that you spend now at a particular place, that is going to be lesser. The same goes with here. So what happened? The heat that was released, some of it was taken back by water in this liquid state, and it used that heat to convert liquid to vapor, right? So now lesser heat was released into the atmosphere. Therefore, this heat is known as the net calorific value. This heat, when water we get in vapor state, that is known as the net calorific value. So this is basically lesser. NCV or net calorific value is always lesser than GCV. Why? Because NCV is the heat that is released after some of the GCV has been absorbed by water to convert its state from liquid to vapor. All right, liquid to vapor. So this is the formula for GCV and NCV, but you will understand this more clearly once you are done with thermodynamics and you understand these concepts of latent heat, all right, sensible heat. When you understand all these concepts, then you will be able to more clearly relate to these concepts. So for now, I'm not going through too much of detail of this. Just understand why is NCV lesser than GCV. All right. Then, two very important concepts which most of the people they get confused with. All right. All the products of combustion include gases and water. All right. So fuel, it basically contains carbon and hydrogen. Right. Apart from that, it might contain sulfur as well. And since you obviously supply oxygen, so it's oxygen, and oxygen it comes from air. So that along with oxygen, it also gives you nitrogen, right? So all these 5 things might be present in the starting. All right. So when this combustion takes place, then after the combustion takes place, we'll get carbon monoxide if the combustion was incomplete, carbon dioxide if the combustion was complete, sulfur dioxide, sulfur gets oxidized, unreacted oxygen, nitrogen, because nitrogen has no role. So as it is, it will come back. Whatever was the nitrogen that is supplied, same amount of nitrogen you'll get over here. And of course, water vapor. Now, if we consider only these gases, that is carbon monoxide, carbon dioxide, sulfur dioxide, oxygen, nitrogen, that is all gases except for water. All right. In that case, these gases are called as dry flue gases. All right. These gases are called as dry flue gases. All right. And if these gases and water is included as well, in that case, they are known as wet flue gases or stack gases. All right. Stack gases. So in that case, you consider water as well. So if you don't consider water, it's dry flue gas. If you consider water, that is going to be wet flue gas or stack gas. And also you people have studied, actually you people solved a problem of GATE in which you people considered SO2 free, no, SO3 free bases, right? So now you people have probably understood that how do we take bases as SO3 free. So whenever we are going to say that we have dry flue gas composition as this, then we are going to assume that the total dry flue gases, that is except for water, whatever is remaining is your P. And let's say you are saying that 10% is the composition of carbon monoxide in this dry flue gases, then carbon monoxide is going to be 10% of P, where P is basically the sum of carbon monoxide, dioxide, sulfur dioxide, oxygen, and nitrogen. It's not going to include water. But if you're considering stack gas or wet flue gas, then in that case, it is going to consider all of these. So hope you people could understand the basics behind combustion. All right, certain basics that were involved in combustion. All right. So now, once you're done with this, let's go on to material balance involved in combustion. So material balance in combustion is again same as what we did for previous reacting systems. Just in combustion, there are few more reactions involved. So this becomes slightly complicated. All right, but it's just as similar. Just go step by step in combustion reactions as well. And then we'll be able to solve the problem easily. All right, so all the steps involved are same as material balance involved in material balance with chemical reactions. All right, so you don't need to worry about steps of combustion, steps of material balance. It's the same. All right, everything is the same. All right, remember one thing, although over here in combustion there is a concept of excess air. All right, so we discussed, right, percentage excess. So here we basically supply air in excess. We supply air in excess because we need to ensure that the combustion is complete. Although in very rare cases you get completely 100% carbon dioxide. Some amount of carbon monoxide is always present. But yeah, we still supply excess air in order to ensure that maximum of the combustion that takes place is complete, right? So for excess air, you usually are given with percentage excess air, or you need to calculate the percentage excess air. So it's either of the two things. So you're going to use the formula that we derived using B. So B supplied is B theoretical into 1 plus percentage excess by 100. So that formula is going to be useful over here when we deal with percentage excess air. All right. So remember, air contains 21% oxygen by mole and 79% nitrogen by mole. And if we go by weight, this was by mole. So if we go by weight, then it contains 23% oxygen and 77% nitrogen. All right, that is the weight percentage. All right, so remember this thing. So in that case, if we have, suppose if we manage to calculate oxygen, I'll just give you this. So suppose if we somehow calculate oxygen, all right, oxygen supplied, all right. Suppose if we calculate oxygen supplied, so that is basically 21% of air supplied. So let's say air supplied is X. So it's 21 by 100 of X, right? So from here you'll get X as oxygen supplied upon 0.21, right? 0.21. Then nitrogen supplied is going to be equal to 79% of this. So 79 by 100 into X, or 0.79 into X. Now X you have already calculated it as oxygen supplied by 0.21. So that is equal to 0.79 upon 0.21 into oxygen supplied. So this is how nitrogen supplied and oxygen supplied are related. All right. So if you get oxygen supplied, then you can calculate nitrogen supplied from that. If you get nitrogen supplied, then you can calculate oxygen supplied from that. So our oxygen supplied would be 0.21 into nitrogen supplied upon 0.7. All right. So this way. And similarly, you can go with mass basis, weight percent basis as well. So in that case, it would be nitrogen supplied is equal to 0.77 upon 0.23 into oxygen supplied. All right. So you can go with that. Okay. So this is another information that I could give you about combustion calculations. And apart from that, I don't think there's too much to inform you. You already know what is theoretical demand. You already know what is excess. You already know what is conversion. So all these basic concepts you already have in mind. Now, in the next video, we'll be solving a few problems based on combustion. So when we'll be solving those problems, you'll get a better idea about combustion based problems. So these were some basics that I could supply to you people, so that when we'll be using these concepts over there, or when we'll be using these formulas over there, so you should not be confused about what to do and why is he doing that. So you should not be confused about that. That is why I have given you these formulas. So make sure that you're very clear with this video before you start the next video. All right, the next video would involve problems based on combustion. So please make sure that you know these concepts that have been mentioned over here. All right.